So we're gonna stop here tonight, but that was a really good test. What's up, YouTube fam? Today is a very fun day for me. We are programming the book Moto, voltage, current, etc. into a state of charge meter. So I have installed the state of charge meter here. And now the question is, let's get this sucker all up and running, right? There we go. So there's our state of charge, or there's our thing with our state of charge. So I'm going to program it so that 51 volts equals full and see what we can get going there. So what's going on over here? Let's talk about what's happening over here. Okay, so coming in nice and tight on these guys here. This is my charge controller. This is the BMS, or battery management system. Together they operate this wire here, CAN bus wire, communicates, sends signals between the two to talk about the battery state of health, the charging, the discharging, and so together with this communications cable that plugs in right here, we'll run the communication cable to my computer, and let's see what we got here. Fired up. Okay, so really all we care about is this black screen right here. Let me break this down for you. So it's saying the voltage of the pack is 50.45 volts. We have 15 cells in our pack, and the distribution of voltages amongst those cells averages between 3.387 to 3.393. So it's a pretty tight window. They're pretty well balanced. For the time being, please disregard the average and the standard deviation. I hooked up the last two cells incorrectly to the battery monitor, and it's giving a slightly inaccurate reading on those two cells, which is throwing off the average and the deviation. Don't worry about it for now. I fix that later. So the cells here are all about 3.4 volts each. And when they reach that 3.4 volts, the charging should stop. So I programmed that into the EVCC that when this pack reaches 51 volts, which comes from 3.4 volts per cell times 15 cells, 51 volts, that the charging should stop. Okay, so we're back here. I got my directions. So what we're going to do now is I want to set up this so that when it reaches 51 volts, it stops. This is not 100% accurate, but either way. So we're going to come here to menu. We're going to long press the menu button. Alright, come over to function, and we gotta go through all the functions. Here in section 1.0 through F1.6, this section is all about getting the monitor to recognize what is considered 100% charge and what is considered 0% charge. And there's a bar graph on the monitor that looks like this. And getting that bar graph to synchronize has been an ongoing struggle for me. So first one is, what is the float voltage? Well, with lithium batteries, the float voltage is the same as the battery full voltage. So that's 51 volts. So we want to, let's see, enter, and make that 51. Okay, what else do we need? Let's see, not that. Section 2.0 through 2.6 are all about a low battery indicator. And this would be like your gas light coming on your car. In fact, if I had had more time, I would have wired one of the two alarm outputs to drive an LED light on the dash. Low voltage battery alarm. Let's make it 3.0 volts times 15. 45 volts. 45. Okay, so let's lower this to 45. Alright, great. Then, low battery alarm. Section 3.0 through 3.5 are all about critical low battery voltage. You see, just because the battery monitor is showing 0% stated charge does not mean the batteries are at 0 volts. Rather, the battery pack operates in a safe range of 45 volts to 51 volts, with 45 volts being like 0% stated charge and 51 volts being like 100% stated charge. So if the voltage gets too high, for example, above, say, 55 volts, there could be permanent damage, or worse, these batteries could catch fire and explode. And conversely, if the battery pack gets too low, for example, below 41 volts, the batteries could be permanently damaged and become unusable. And in case you were wondering what happens between 41 and 45 volts, and again between 51 and 55 volts, I wouldn't classify that as critical danger, but I would say it puts a lot of stress on the batteries, and if done repeatedly over time, the battery's ability to store charge will degrade more quickly over the months and years, shortening an otherwise possibly 10-year lifespan that I would expect from these cells. So back to section 3 here. When should an alarm audibly sound to alert the user of a critical pack stress due to undervoltage condition? Well, not 41 volts, because that's too late. 42 would be pretty good. But since there's no way to disconnect the batteries and stop any parasitic drain, let's be ultra conservative and let's just set it at 45 volts to give the user plenty of buffer. I'm not sure why there's two separate low voltage alarms here. Since I'm not sure, I'm just going to set both of them. Cool. High voltage alarm. Section 4.0 through 4.5 are about critically high battery voltage. And just because the stated charge is at 100% doesn't mean the battery voltage can't go higher. It can. It will just put stress on the battery, and at a certain point that stress will become critical and damage the battery, or worse, cause explosion or fire. So when should an alarm audibly sound to alert the user of a critical pack stress due to overvoltage condition? Well, not 55 volts, because that's too late. And 54 volts would be good. And since the charger is programmed to disconnect at 51 volts, and it's highly unlikely that the pack voltage would ever get above that, I'm going to set it at 54 volts. 4. Overshot it. Okay. Cool, there we go. And then what else do we got here? Section 5.0 through 5.5 are programming the battery properties. This should probably be the first section in my humble opinion, but here it is near the end. So the battery manufacturer rates my batteries as 100 amp hour capacity with continuous discharge rate of 1C. So here in section 5.0, we set the rated energy to 100 amp hours, which I already did because, again, this should come first. And then section 5.1 has to do with the nominal continuous discharge rate. And then I believe in order to express the C rate in hours, you take the inverse of the C rate. So 1 over 1C equals 1 hour. You can see here that I already changed function 5.1 to 1 hour, so nothing to do here because, again, this should come first in my humble opinion. Okay, I think that should do it. We have successfully programmed this battery monitor, so now we just need to do a long press to save. There we go, and now it's saved. So when this hits 51 volts, the monitor should register the battery as full. So let's compare voltages now. We've got different volt readings on different battery monitoring systems. This one is saying 50.8 volts, and then I've got a supplemental monitor over here. The charge control indicator is on the front face of this box and is currently flashing green. So how this charge controller indicator works is that the charge controller has its own built-in sensor that sends a signal to the LED, which flashes red when it's below 80% stated charge, yellow above 80% stated charge, and green above 99% stated charge. It's actually not very accurate, so let's look at the monitor on the top of this black box, which is a cheap Chinese-made battery monitor. Now looking at this supplemental monitor, we see that my pack voltage is at 51 volts and the state of charge indicator is only halfway full. And that's because I haven't programmed that part yet. Now let's see what the BMS or battery management system has to say about my voltage. And right off the bat, I can see that cells C8 and C19 are still not correctly installed. And I need to redo the wiring to get an accurate reading on those cells. Before I go, let's just see how this BMS reading is. I'll do the command SH, and we have 50.58 volts. That would explain why it's still charging. Let me do some back of the napkin calculation. If we assume that the actual voltage of C8 and C19 are 3.395, which looks to be the true average, then that would mean that the actual pack voltage is, 0.141 plus 0.260 equals 0.401, and then add that to the total pack voltage. I have 0.58, and that gives us a total pack voltage of 50.98 volts. So pretty full. Okay, so we can see that almost all the battery cells are at 3.4 volts each. This means we're in the final stages of the absorption charge, which means charging with a constant voltage while current decreases until it peters out. The reason current decreases until it goes to 0 amps is, one, the battery's capacity to store charge is saturated, and much like a capacitor, currently asymptotically approaches 0 as the charge is saturated. Two, even if the batteries are not saturated, as the voltage of the battery pack nears the voltage of our charging supply, those values equalize and current will stop flowing from high electric potential to lower electric potential.
Yes, science!
This charger is programmed to call charging complete when the current falls below 3 amps. No other condition will satisfy a complete charging cycle. The only other way for charging to stop is for one or more of the cells to log an error, such as voltage that goes outside our safe range. Finally, let's review what I set the voltage safe range to be in our battery management system, BMS. The configuration consists of first the low voltage alarm, or LVC, which triggers if any single cell falls below 2.8 volts. The next one, high voltage alarm, or HVC, triggers if any single cell charges above 3.6 volts. Low voltage alarm clear, or LVCC, turns off the alarm when the cell voltage is restored to 2.9 volts or higher. High voltage alarm clear, HVCC, turns off the alarm when the cell voltage falls back below 3.5 volts or lower. Balanced voltage cutoff, BVC, means when the voltage of any cell is above 3.4 volts, the BMS sends a signal to our charge controller to lower the current to a trickle charge, which just maintains the battery against parasitic losses. BVmin is the minimum floor of 3.0 volts, at which the BMS will try to balance the pack by draining the cell that has the highest charge. As long as the voltage is above 3 volts, it will attempt to do this. And second to the last, thermistor max, or TH max, is set to 50 degrees C. If the temperature rises above 50 C, the charging will stop. An alert will sound. And then finally, the following options are enabled. 1, balance cells on discharge, and 2, the built-in CAN bus termination resistor is active. Well, that all looks good. So now let's switch my EVCC, or EV charge controller, and check out those configurations that I programmed. I just need to move the plug from here to over here. Come back to my laptop, press enter, and now we're in the EVCC interface. The interesting configs here are the max voltage at 51 volts, max current at 25 amps, as well as charging stops if the current falls below 3 amps, and finally charging will stop if charging goes on for more than 8 continuous hours. Since the charger is currently active, let's pull the charger and see the stats in progress. Alright, I see the charge voltage is at 51.1 volts, and the charge current is fluctuating between the upper 6s and lower 7 amps. Got it. This stage of charge is called the absorption charge stage, where voltage is held constant and current falls in a fairly linear fashion over time from max current to 0. Since the charge controller seems set to turn off when the current falls below 3 amps, we still have a bit further to go to finish our charging here. Now let's see the reasons that this charge controller terminated charging. Starting at the top of this list, the last charge was interrupted when I pulled out the plug after 14 minutes of charging. It looks like the next 10 attempts to charge prior to that were unsuccessful due to unresolved communication errors between the EVCC and the charger itself. Probably because I needed to resolve a wiring issue that left the EVCC unpowered when the AC plug was inserted, but my 12-volt key was switched off. Then lines 11 through 15 show that I had a single bad cell. The story behind this cell, number 16, was its terminal popped off. After the manufacturer refused to replace the cell, I hired a welder to weld the terminal back on, and well, I'm guessing that using an arc welder on an LFP battery was a bad idea because the battery never worked quite right after that. It kept overvoltaging as shown in the HVC errors on lines 11, 14, and 15, or going down to near 0 volts and hence was counted as missing in the sales census, lines 12 and 13. This single cell was completely out of balance with the rest of the pack, and ultimately I had to pull that cell and rewire this from a 16 cell pack to a 15 cell pack until a new cell could be ordered to replace that 16th bad cell. Finally, let's take a snapshot of this charging cycle. The state is currently charging with constant voltage. The EV supply equipment, or EVSE, that's code word for the charging plug, is connected and locked. And then the voltage is 51.1 volts, which we already knew. And the current is around 7.0 amps. This charging cycle, we've added 213 watt hours, have been added to the battery pack over the last 29 minutes. Cool. Very cool stuff here. So the question is, did I set this up right? I'm holding the throttle constant. If I let go, it'll release. The battery voltage is holding steady at 49.1. Here's what's significant. This is a 48 nominal voltage battery pack, 48 volts nominal. 3 volts above that, 51 volts is considered fully charged. 3 volts below that, 45, is considered fully dead. So this has a play between 45 to 51. I started off at 51, maybe a little less than that because I was monkeying with it. And then I'm holding the throttle steady at 15-ish amps. This is a 100 amp hour battery. So thus far, I've used 2 amp hours. So that should mean the battery percentage, this is easy math, since it was a 100 amp hour battery, 1 amp hour equals 1% of battery. So if I've used 2 amp hours, probably plus a little more, I should be down around 2% of battery, which is about what we're seeing here. So this is good. And so the battery percentage is tracking pretty well with the amp hours used. And then this is a timer that says at this particular speed, this is how much longer we can go. Now there's no rolling resistance, there's no anything resistance because the car is lifted off the ground. We're just stationary in my garage. It's probably not safe, but whatever. So I'd be interested to see how many hours this could go. 5 hours, 22 minutes with no resistance. How long could it go? And what speed is this, right? We got to put in a GPS to figure that out. But either way, this is pretty cool. So I think we did this right. I'd love to just hold the throttle here and come back in 5 hours and see what it is. But I don't know how to hold the throttle. So I think we'll stop here. I'm really digging this though. 2.4 amp hours. Cool, I like it. Yeah, this is good. This is real good. And I let go and it automatically turned off. So we're gonna stop here tonight, but that was a really good test. And you can see the voltage jumps back up a little bit when you release the throttle. Well, that's all for today, folks. If you found this video helpful, please smash that like button. And more importantly, please subscribe. That's how we make more videos. Until next time, this is Austin EV Only.